momentum and impulse. And momentum, linear momentum, is defined as the mass of the object times its velocity, instantaneous velocity. So the momentum here is an instantaneous quantity at a particular moment in space and time. So this is the momentum of the object at an instant. It's an instantaneous quantity, and it's a vector quantity, meaning the direction in space is really important. So you can always talk about direction and magnitude for the momentum. And its units is units of kilograms, its SI units, kilograms, meters per second, because its mass, kilograms, velocity, meters per second. And we identified that the total momentum is the sum of the momenta of the constituents. So the total momentum of a system made up of many objects is the sum of the momenta of the constituents of the system. I.e., if I have multiple objects with masses, different masses and different velocities, so object 1, object 2, mass, velocity, etc., then the total momentum is the momentum of the first object plus the momentum of the second object plus the momentum of the third object, and so on. So I can just add them, but these are vector quantities, so I have to add them as vector quantities. So that's the story of the momentum. And then there was another story about something called the impulse. And the story of the impulse said that anytime you accumulate some force over some time, that's called the impulse. It's basically, typically we think about it as the net force, the average net force. We can talk about the impulse of an individual force, but when you talk about the impulse being applied to an object, you typically talk about the net force. So the impulse is about the accumulation of force times the time of the application of the force. So this takes time. During time of interval, during a particular time interval. And that's why sometimes we call it contact time, or time of contact. So the impulse happens during a time interval. The momentum was instantaneous, but the impulse happens over time. This is a quantity that you calculate over time. It's also a vector quantity. So the direction matters. To the left, to the right, up, down, front, back, it matters. What direction the force is, that's the direction of the impulse. It also has units of Newton seconds, which can be written as kilogram meters per second. So its units are also Newton seconds or kilogram meters per second. They're the same thing, they're equivalent to each other. We've shown that. Now there's one thing about impulse that we haven't talked about yet that I'd like to mention at this point, which is that sometimes we make a distinction between impulse generated by external forces and impulse generated by internal forces. Typically, we don't really worry about this at all. We don't really consider this when we're thinking about problems at all, because it doesn't do anything. It does not cause a change in momentum. For example, I'm sitting here, I'm not moving at all, and then I can apply one force from one muscle, on another muscle or on a bone. These are forces from parts of my body on another part of my body, right? We call these internal forces. So any impulse that is generated there is not going to change my momentum. It's not going to move me. I have to make an impulse against an external object. I have to push against something to start to change my momentum. So external impulse is the thing that is going to matter to us. So to make the definition again, to make the definition really robust, an internal force is a force from one part of the system on another part of the system. An external force is from an outside environment on one part of the system. And then we also talked about the momentum impulse theorem, or the impulse momentum theorem, which is analogous to the work energy theorem. Remember, the work energy theorem said that the work done is the change in energy. This is analogous to it. It's saying the impulse is the change in momentum. So momentum at the beginning, momentum at the end, the impulse is the thing that happens between them. The same thing with work and energy. Energy at the beginning, energy at the end, the work happens in between them. Just like bank account at the beginning, bank account at the end, transactions happen in the middle. So the momentum impulse theorem said that the external impulse, so far we've been saying the impulse, but we're just going to identify it as the external part of it. So the impulse done by external forces will change the momentum of the system. So if I am the system, that means every part of me is part of the system. So me pushing against myself can never move me. I have to apply an external impulse, or some object has to apply an external impulse to me. So when I push against the wall, that means the wall is pushing against me, and the wall pushing against me is what moves me. I don't know who I heard this from, but they do this trick with, I think I read it in some interview with some astronauts. When they go to the International Space Station when they're rookies, one trick they play on them sometimes is they take them out of their beds and they just put them in the middle of the International Space Station, so they can't touch any walls. And then when they wake up, they realize that they're right in the middle of the International Space Station, but they can't move. They can't move themselves because you can't touch anything. So you can move your arms, yes, you can flail around, you can move your legs, but you just can't move within the International Space Station because you have to change your momentum relative to it. So you have to push against something. Or you have to, maybe take something off and then split yourself into two. So one part of you would go one direction, another part of you would go another direction. So maybe you take a jacket off or pants off or your shoes and you throw them in one direction so that they move in one direction, you move in the other. So you're doing an external force against. So you have to divide yourself into two pieces if you want to do that. If you want to change. So this is really what we've talked about so far. And that means then the other part that we've done so far is to say that suppose there is no external impulse. So just like if you think about a problem, think about two objects coming like this, one object moving in this direction, another object moving in this direction, and then they collide with each other. And then now let's say they're moving in opposite directions. Now during the collision, so right at this point when they're colliding with each other, they're exerting forces on each other. So these here were velocities, but the arrows that I'm drawing here are forces. So force of 1 on 2, force of 2 on 1, the forces they're exerting on each other right at the moment of contact. Now the question is, are these forces internal or external? And the answer is that it depends. If this is my system, just this one ball, then the force of ball 2 on ball 1 is external. So if I call this A and I call this B, call this A and B balls. So this is the force of B on A. And this is the force of A on B. And these forces, the question is, are they internal or are they external? That's the question we're trying to answer. And we're saying that the answer really depends on what's your system. If I'm just thinking about the system as being A, let's consider that for a second. So my system now is A. A was moving with some velocity like this. And then some force happened to it. Where did this force come from? It came from B. Now B is not part of the system. So this is an external force. And that external force obviously changed the momentum of A, because the momentum of A was to the right and now it's to the left. So its momentum definitely changed because of this external force. If I think about B on its own as the system, so this here is my system. So B was coming in with some momentum in this direction, and then some force happened to it. Is this force internal or external? It's external because it's coming from A on B. A is not part of the system. So that means that this force is going to change the momentum of B like this. But if I tell the story in which A and B together are the system, then the force of B on A and the force of A on B are both internal forces because it's part of the system on another part of the system. That means the total momentum of the system is not going to change. So the total momentum before collision is going to be the same as the total momentum after collision. In other words, mass A times its velocity plus mass B times its velocity. That's the total momentum, right? This is how we say total momentum. Before the collision has to be equal to the mass of A times its velocity plus the mass of B times its velocity after collision. And that's called the conservation of the momentum of the system made up of the balls A and B. Let's talk about the types of collisions. I'm going to tell you exactly what the rules are, but I just want to chat with you for a second. Like suppose you think about a golf ball, that hits the ground versus maybe a basketball hits the ground, maybe versus sort of a deflated basketball hitting the ground. Right? Let's just think about these three different scenarios. In the golf ball hitting the ground, the golf ball has a certain kind of finish on the outside, certain kind of material that makes it such that when it bounces off, it typically comes back to almost roughly the same height that it came to, that you dropped it from. A basketball typically bounces to a little bit less, unless you push it, right? But if you just drop it, then typically goes back to a height that is a little bit less than where it started from. And then a deflated ball would just completely flop right on the ground. It wouldn't even bounce at all. These kinds of collisions we call inelastic. And this kind of collision we call elastic. Let me explain to you why. Where does the collision happen? The collision happens here right at the ground, between the ball and the ground. So this ball dropping from a certain height, it has some gravitational potential energy here. And then that gravitational potential energy gets converted into kinetic energy. And then kinetic energy here right at the ground, if I keep the same kinetic energy coming back, I will come back to the same gravitational potential energy, meaning the same height. So if right at this moment, kinetic energy is conserved, so this collision doesn't take any of the energy, then I'm going to bounce back to the same height. But if the collision with the ground takes away some energy, so the kinetic energy is no longer conserved right at the collision, which is obvious in this case, but more obvious in this case, right? It completely, all of its velocity was dissipated in the collision here. So the kinetic energy is not conserved in these collisions. That means they're inelastic. So really the distinction between them is that in elastic collisions, kinetic energy is conserved in addition to the momentum. The momentum, of course, is conserved in all kinds of collisions as long as there's no external force. So in all kinds of collisions, momentum may be or may be not conserved, but this is a separate story. So we're saying that momentum is conserved when the external impulse is equal to 0. That's just a done deal. We're not debating this anymore. We're not thinking about this. Momentum is concerned in this case, is conserved in this case. But the question now, is the kinetic energy also conserved or not? Kinetic energy, if you remember, was half the mass times the speed squared. And for elastic collisions, kinetic energy is conserved. For inelastic, the kinetic energy is not conserved. So that's how you recognize the collisions. What do I mean by kinetic energy is conserved? I mean, if I have two objects that are colliding, so just like the previous slide, mass 1 has velocity 1, and then it collides with mass 2 that has velocity 2, then the conservation of kinetic energy, what it really means is the following. It means that the total kinetic energy before the collision is equal to the total kinetic energy after collision. For some reason. So that means half the mass 1 times the speed 1 squared plus half the mass 2 times the speed 2 squared before the collision has to be equal to half the mass 2 times the speed 2 squared plus, half the mass 1. So it's the same quantity before and after, it has to be the same. That's what conserved means. Conserved means before equals after. This here is conserved. So this is what I mean by kinetic energy is conserved. The total kinetic energy. So this is kinetic energy total of the system. This is kinetic energy total of the system. Before equals after, that means it's conserved. So that's it. These are the two slides basically that you need to know for the momentum and impulse. Definition of momentum, the definition of the impulse and what it's about, how they're related to each other with the momentum impulse theorem, and how that manifests itself in conservation of momentum that happens when the external impulse is 0, meaning no forces from the outside are acting on the system. But if the forces from the outside are acting on the system, they will change its momentum. And the kinds of collisions, you have two kinds of collisions depending on, in addition to the momentum, whether the kinetic energy is conserved or not.